It's been a fun time. And this seminar series online has been in some ways just as great as it's been in person. But yeah, we missed the in person. Today we have a great speaker, our own Shannon Ray, who got his physics degree from Wichita State University in 2010. He was a McNair Scholar with us as well. He worked with Professor Meyer and I on several trips out to the tentative Auger North area and the border of Colorado and Western Kansas. And then he went off to Florida Atlantic University, got his PhD there, and is now working at the government lab with the Air Force doing his gravitation studies. And so it's a great pleasure, and it's very nice to see Shannon again, and hopefully we'll see you in person after this pandemic is over.
Oh,
So
definitely.
please join me in all welcoming Shannon for his physics seminar today.
Great. Yeah, I'll definitely stop by when I come to visit my family. All right, so share screen. All right, everybody see it?
Yep.
Okay. So today, thank you, Nicholas, for inviting me. I'm really happy to be here to talk to you guys. And today I'm going to be talking about my work on the purification of three-level quantum systems and what I call the surfaces of ignorance, where essentially we'll be using differential geometry and differential manifolds to bridge an understanding between information entropy and thermal entropy. So to give a little background before we get started, as was said earlier, I got my PhD from Florida Atlantic University back in 2017 under Warner Miller, where I studied computational geometry and general relativity. I had a couple of computational geometry projects involving Ricci flow and isometric embeddings. And I studied the energy of pure gravitational fields using the Wang and Yau quasi-local energy. I got my Bachelor of Science from Wichita State in Physics and Mathematics back in 2010. And as you can see, my research interests, currently I'm interested in quantum fidelity, channel, and state discrimination. Of course, I was interested in classical gravity and isometric embeddings and computational geometry. My thesis, my dissertation was essentially stitching together these two papers, one on something called the adiabatic isometric mapping algorithm, where you take triangulated two surfaces and embed them in Euclidean 3 space. And the other one was studying the Wang and Yau quasi-local energy for Kerr black holes rotating near their maximum angular momentum. Since graduating, I am now working at the Air Force Research Laboratory with Paul Alsing's group. And one of the first publications I got working there that we did together was on the maximum advantage of quantum illumination. That got accepted in the PRA, where it was chosen as an editor's choice paper. And I also wanted to highlight a paper that I did with Carlo Coffro and Paul Alsing on the geometric aspects of quantum evolutions. There's more publications, but this is as much that could fit on the slide. So this is what I chose to present. Okay, so the outline for the talk, we will first start off by giving an understanding of the, working toward an understanding of the Ohmen-Joseph fidelity. And we start from there because that was the original starting point for this work, which kind of guided us to where we are today. After that, we'll talk about the fact that we had to work outside of Euclidean 3 space for our analysis, which introduces the idea of Lie groups and fiber bundles, which is where we work. And then finally, we'll present the calculation of the purified manifolds. So, and then we'll just, end with a conclusion. So yeah, so working toward a physical understanding of the Ohmen-Joseph fidelity. So this section, we're going to start off by motivating the setting of our calculation and then go over several interpretations of the Ohmen-Joseph fidelity to kind of emphasize the difficulty and nuance in understanding it physically. So starting off, in our analysis, we are working in a space where we assume that all of our density operators are diagonalized. So at the top here, you can see rho and sigma as our diagonalized density operators. And the advantage of that, as you can see in this figure, is that each density operator can be understood as a point on a probability simplex, where the bases of the simplex are the eigenbases, which represent a set of possible outcomes in an experiment. And each point on the simplex represents a probability distribution associated with those possible outcomes. Um, another thing that we did, as you can see, we're working in R3. And to do that, we set all of the phase angles on our unitary transformations to 0. And so doing that makes it to where we work in this restricted space of quantum states where all of our inner products are real. So everything's real. And we think that that's fine to do because one of the things that we wanted to get out of this is have a geometric approach that can help us visualize and to help us with visualization so we can understand the Oman-Joseph fidelity better. And so, we're working this restricted space, but we think that's okay because the functions or studying the Oman-Joseph fidelity should be independent of the states that you're studying. And so to kind of set up how you get a quantum perspective from what appears to be a classical setup, because both of these simplices look like classical objects. And so to do that, we start off with this first definition of the Oman-Joseph fidelity. There's nothing special about this definition. There are many definitions. This is just one of them that we're using that can help make our point. And that point is when you are trying to compare density operators on two different simplices, if you were to just take the trace of the square root of rho and the square root of sigma, that gives you a lower bound on the Oman-Joseph fidelity. And the only time that this is exact is when this Pij, which is a doubly stochastic matrix that allows you to map between distributions defined on each simplex. So you see that you can take sigma and get sigma prime from applying this Pij operation. When that thing is just a delta function, then what we have is the two density operators, rho and sigma, they share the same eigenbasis. And in that context, then what we recover is just a classical fidelity measure. So everything in that instance is classical. It's when the two density operators do not share the same eigenbases, i.e. when Pij is not a delta function, is when we are now in the realm of quantum and we need the full machinery of the Oman-Joseph fidelity to compare quantum states. And so one of the standard definitions you'll see of the Oman-Joseph fidelity is given by this alternative definition 1. And just looking at that thing, it doesn't really glean any obvious physical interpretation or understanding. It actually looks quite convoluted and hard to understand. And so we wanted to focus on the alternate definition 2, which is what we'll be focused on throughout this paper, where we can see that the fidelity is defined as the maximum overlap between purifications of rho and sigma. So to define a purification, essentially what you can do, we can look at this figure. You can imagine that the density operators, rho and sigma, are defined in this base space. And in our calculation, that base space is R3. And what you can do is you can take a reservoir space, HR, and you can make a composite space, a larger dimension composite Hilbert space. And in that Hilbert space, there exists a set of pure states where if you take one of the pure states, like this phi of rho, you construct a density operator out of that pure state. And if you trace out the reservoir, then you get back the density operator. And so in this case, there exists a set of these purifications, and that's what the vertical lines represent. It's a set of these purifications. And when you're comparing these, you're essentially going through this set and you're looking at the two that have the maximum overlap, and then that's what we're defining as the fidelity. And so something about this in terms of understanding this physically in terms of measurement statistics in a lab, it's not particularly obvious why looking at overlap between purifications should give you some understanding of fidelity. And so we wanted to try to motivate our calculations to see if we can have a better physical understanding of what that process is. And hopefully I'll convince you guys of a good physical interpretation of this higher Hilbert space and these purifications, what they represent. And so for completeness, I just included this third definition of the fidelity, where it's essentially you compute it like a classical fidelity. So on the left here, we see that this classical fidelity is what you would compute for two classical probability distributions defined over the same set of possible outcomes. And so for any density operator, you can construct a classical probability distribution by projecting the density operator over a complete basis that spans the space. And so when you do that, you can get you have a set of observables. Like there are many observables that you can do this projection process on. And so the fidelity is defined with respect to the eigenbases that's given from the spectral decomposition of this geometric mean operator, which again looks really convoluted and it's kind of hard to understand or interpret. But if you do a spectral decomposition of that, where you get the eigenbases that represent it, then you use those to construct classical probability distributions and compute the classical fidelity, then you recover the Ohmen-Joseph fidelity. And so this is another aspect that we're not going to focus on too much in this talk, but we have studied it, and I think there is a decent interpretation in terms of these fibers. But this is just for completeness. So, all right. So now that we've kind of set up our problem and what we're going to be focusing on, I want to discuss the fibers and how they're and how they're used in this work. So in this section, we will introduce the concept of fiber bundles, and we will just give several examples to hit home the context to which and how they're used in this calculation. Okay, so looking back at the figure that we started off earlier, where I was defining the fiber or the second alternative definition of the Ohmen-Joseph fidelity that you can see at top, I want to use that image, this image, and look out how it's analogous to the concept of fiber bundles in general. So in this case, the base space that I mentioned before, HA, this is the space where the density operators lie. And the space E, and when you talk about in terms of fibers, this is the complete space. So in our analogy, the complete space is the higher Hilbert space that you get from taking the tensor product between these two, these two copies of R3. And the fibers, they are given as a set in the total space, a set in E that when given an equivalence class, map to a single point in the base space M. And so in this case, the purifications are analogous to the fibers, and the density operators are analogous to the points in the base space. And so to continue to kind of do some more examples to get people familiar with fibers and how they're used. We start off with a total base space, a set from 1 to 11, which represents coincides with a specific shape. And given this set of shapes with varying colors, you can define an equivalence class, say the set everything that has the same shape, and that equivalence class creates a quotient space or a base space M, where you go from having 11 points to only 3, because all triangles get mapped to one thing, all squares get mapped to one thing, and all circles get mapped to one thing. And you can also do the same for like an equivalence relation with respect to color, for example. And then that brings you to a lower space that has less points than the higher space. And this process is essentially the process of going from higher resolution data to lower resolution data, because when you create this equivalence relation, each point in the base space is only defined with respect to that equivalence relation. So for example, with these triangles, you lose the fact that this is a red triangle, for example. So you go from a higher resolution data to lower resolution data. Going to another example to try to connect this to Thermo. And this is actually an example that I remembered from my classical Thermo book when I took the class at WSU with Dr. Ho. And so I just decided to use this here. And in this case, you're flipping 3 distinct coins. And for each sequence, like there are a set of sequences, you can look at the macro information as being sequences that have an equivalent number of heads. So that would be the information in the base space. And then, of course, each sequence that satisfies that information gets mapped to the same point. And so the space, the actual sequences, this represents like the micro information, the information that is higher resolution, and then the number of heads in the base space represents your lower resolution, where omega is the multiplicity associated with the macro information. So you can see that we have, and if you have two heads, for example, there are three different sequences that have that, or three different microstates that have that equivalent macro information. And so to tie this to Thermo, we see that we have omega, which represents the multiplicity associated with the macro information. And in this case, what we're saying is that these fibers like the micro information are symmetric with respect to the macro information that's given. And so if we're looking at like a simple system in Thermo, the micro information may be the phase space parameters of every particle in the system that you're looking at. And the macro information could just be something like the energy, volume, and number of particles. And so again, because we're relating these fibers with purifications and microstates and macrostates, this is how I'm setting up the relationship between information entropy and thermal entropy. So moving on, I call these, now we're gonna set up the calculation. So in this section, we're gonna do a little bit more motivation of our calculation. Then we're just gonna explain the calculation, and then we'll just discuss the results. So first off, we're gonna start by kind of starting off with an understanding of information entropy. And in this case, the way that I would think of information entropy is it tells you something about your certainty of a measurement outcome. So a phrase that I came up with was information entropy is a measure of one's location on the spectrum between uncertainty and information. So to make that clear, I wanted to use a simple two-level system example, so the binary entropy example, where it's like flipping a coin, and P represents the probability of the coin landing heads. And in this case, if P is equal to 0.5, then you are maximally uncertain, meaning you have no idea what how the coin will land, whether it will land heads or tails. But if the entropy is 0, so if P is equal to 0 or 1, then you're completely certain that it will land heads or tails. And of course, every value of the entropy in between those two values has a varying degree of uncertainty or ignorance as to what will occur when you flip the coin. And so we see that the your capacity to be ignorant depends on the number of possible outcomes. So in this case, we only have two possible outcomes. And so what we end up getting is this complementarity relationship between uncertainty and information, where the information entropy has to total 1 bit, because you take the log base, you know, it's 2 dimensions, so you take log of 2 with base 2 and it gives you 1 bit. So you're basically splitting up 1 bit between uncertainty and information. And so to kind of explain what it means to be uncertain in this regard, I go to another example. So imagine that this is a table here, and there are two people in a room. Oops. There are two people in a room, Alice and Bob. And Alice tells Bob, hand me the object on the table. And she wants one specific object on that table. And so given that constraint information, the hand me the object on the table, Bob is left in a situation where he has a 1 in 10 chance of picking the exact object that she wants, because each one of these objects are symmetric with respect to the information that she gave. And so you have a multiplicity of 10 with respect to that information. But then she says, hand me a green object on the table. With this extra constraint information, Bob has now gone from a state of 1 in 10 chance of guessing the right thing to a state of a 1 in 3rd chance of guessing the right thing. And so finally she says, hand me the pointy green object on the table. In this case, there is only one object that satisfies that constraint information. And so Bob is now in a pure state where he knows for sure that if he grabs that pointy object, that will be the object that Alice wants. And so again, this is kind of another representation of how the information entropy affects your certainty, which then affects the set of symmetries that satisfy that constraint information, which then gives you your probability of selecting incorrectly given those symmetries. Okay, so now that we've motivated our calculation in terms of relating things to information entropy and thermal entropy, we now want to set up our calculation. Where because we're working in R3, like I said, since everything's diagonalized and we've gotten rid of the phase information, our bases for our eigenbases for our row density operator is just a standard bases given here. And we can relate all of our bases on sigma using this using set of unitary transformations on the row bases. But I probably should have included the sigma stuff because in this calculation, we're actually only going to be concerned with one probability simplex. And so in this case, the symmetry group associated with our space R3 is just given given by the Euler transformations here. And so now that we have that set up, oh well, before we move on, I want to try to emphasize again to make the same analogies that I was making before for the relationship between like fibers and symmetries and the base information. So in this case, we have the base information on the probability simplex, and the surfaces of ignorance, or the manifolds of ignorance that we're going to be looking at, are the manifolds that arise from the symmetries associated with the constraint information provided by the density operator. So in this sense, the constraint information on the density operator are the eigenvalues and the eigenbases, and that makes up the constraint information on the density operator. And you can see that if you have, for example, a point on the on one of the axes, then that would be a pure state. And if that were a pure state, then in the higher Hilbert space where the fibers exist, then you would have a volume of 0. And so these surfaces up here are what we're going to be computing, and they represent the symmetries that exist due to missing information in the density operator. Okay, so now moving toward the our calculation. As we were saying before, the our composite Hilbert space that we'll be working in is just a tensor product between two copies of R3. And so just to get our purified manifolds, we start off with something called a canonical purification, which is phi sub rho. This is a canonical purification. And this is just a standard procedure that I got out of Wilde's quantum information theory textbook. And so you have this canonical purification, which you can find using the square root of rho, where gamma is simply an unnormalized Bell state of 3 dimensions in our example. And so if we want to, so given this one purification, we can get access to a continuum to all of purifications by applying a unitary transformation on the reservoir space. So the unitary is only applied to the reservoir space, and gamma bar represents the set of all purifications that is associated with the Euler angles when transforming the reservoir space. So now we have all purifications that we can have access to. And so now that we have all our purifications, we now want to construct our metric. And so to do that, we do a Taylor expansion where alpha represents the point that we'll be expanding around, psi represents our approximated point, and then we have this differential vector here. And from there, we can simply just go take a first order approximation, subtract the 0th order term to the other side. And now we have our ds that we can use to construct the first fundamental form, which is just a standard procedure for constructing metric components. And so because because we're working in this higher Hilbert space, we have it has a clear scalar product defined on it because all of our states are pure. We have a clear scalar product, which induces a metric. And so these are our metric components using the scalar product in this higher Hilbert space. And so just writing the metric components down explicitly with everything that, with all of our machinery that we've constructed so far, here's what our metric components look like. And so to get the volume, to compute volume, we just take the square root of the determinant of the metric and then integrate over the Euler angles. And so this gives us our volume of these purified manifolds. Okay, so now that we have the volume of the manifolds, we now want to look at these volumes with respect to curves of constant purity. And so to do that, we have these two constraints, one where the sum of the eigenvalues has to equal 1, and the other where the sum of the square of the eigenvalues has to be equal to the purity, where this 1/3 plus n over 15 is just a convenient way for me to take these interval in which the purity is defined and divide it evenly by 10. And it's just convenient for me. There's nothing special about doing that. But when I've done that, we now, given the constraint of constant purity, we now have our second eigenvalue, lambda rho 2, written in terms of lambda rho 1. So our degrees of freedom are lambda rho 1 and n, which determines our purity. So given this construction, we look at the volume as a function of lambda rho 1. And if we look at the figure on the left, the circles represent curves of constant purity on our probability simplex. And so in this case, lambda rho 1 parameterizes these circles where it starts at this point here and then rotates counterclockwise. So that's the way in which these circles are parameterized by lambda rho 1. And it should be noted that in these plots, we're only looking at half circles. So we're only looking at the bottom half of the circle. And you can also notice that in some of these plots, there are these gaps. And these gaps represent the curves that fall off the probability simplex. So they're invalid choices of eigenvalues. And so if we look at this, there's a couple things that are striking about it. One is that the volume oscillates as a function of lambda rho 1. And what this implies is that something like constant purity is not sufficient to capture constant ignorance. Because remember, the way that we're associating ignorance is given the set of purifications, each one of those purifications could be responsible for the information found in the density operator. Because if you take the partial trace of one of them, then of any of them, then it gives you back rho. And so they're all equivalent in that sense. And so you're asking yourself, given all those equivalent purifications, which one is the one responsible for the constraint information? And if you just pick randomly, the more purifications there are, the more likely you are to pick the wrong one. And so that's why we're associating volume with ignorance, because your chance of picking the right one is pretty bad as the volume increases. The second feature that is interesting is that the volume decreases monotonically with respect to different values of purity. So in the upper left corner, we have lower values of purity. And then in the lower right corner, we have an actual pure state where we see that the volume is just equal to 0. So it just goes to 0 volume. And to kind of demonstrate this monotonic behavior of the volume, we took those plots that I just showed you, and I took their minimum and maximum values, and I plotted them as a function of purity. And so to kind of, again, hit that idea home that these things are associated with ignorance, you can imagine that the maximally, uncertain state, the one with maximum or minimum purity here, this would be associated with, like, say, Alice saying, hand me the object on the table. Well, you're maximally uncertain. You have a 1 in 10 chance of getting it right. Then at some intermediate point, say like 0.7, for example, that would be associated with her saying, hand me a green object on the table. It's like, okay, well, there are less symmetries now, and I have a better chance of selecting the right one, but I still have a 1/3 chance of getting it wrong. And then the point where the state is pure, that's equivalent to Alice saying, hand me the green pointy object on the table. It's like, now I know for a fact that I will give you the right object with 0 uncertainty. All right. So one thing that we want to desperately understand is the nature of the oscillation, because again, constant purity, if we're using purity as a measure of information entropy, is not sufficient to show equivalence of ignorance. And so to kind of try to understand why that was, one thing that I did is I looked at I thought maybe that the distance of points on a curve of constant purity, the distance of those points from pure states might actually be some way of explaining this oscillation. And so I simply took for each point the sum of the distances for each point on a given curve. I think this particular plot is for the inner curve, the blue curve. And then what I did is I rescaled those sums. I rescaled them so that they actually matched with the scale of the volume. And what we see is a pretty good match of these two things. And so when I first saw this, I thought, oh, maybe this is the explanation. But as we found later on, this explanation is not sufficient. And the reason why is because one of my colleagues suggested, hey, instead of just looking at purity, why don't you look at these Rengge entropies? And so the Rengge entropy is defined here, where you have Rengge entropies of varying orders of alpha. So you can choose any value of alpha between 1 and infinity. And this would give you, and this is another information entropy measure. And what we find is that when we choose alpha of order 3, in that case, we get surfaces of constant volume. So that means that there's something about the Rengge entropy order 3 that gives you an equivalence of ignorance among points. We don't know why that is. That's still something we're trying to understand. But as you can see, when we go to say Rengge entropy of order 4, we get more oscillatory behavior. And this is true for von Neumann entropy, for any other information entropy measure that we examined. Rengge entropy of order 3 is the only one that gives you constant volume. And so, that's something that we really want to understand. Okay, so now that we've gone over our results and where we are so far, one thing, I had a fun calculation that I wanted to do where we can visualize these surfaces of ignorance. And so starting off with the original metric of the entire 3 manifold, because these surfaces of ignorance are 3 manifolds, they're 3-dimensional manifolds with respect to the 3 Euler angles. And so if I want to visualize these by isometrically embedding them into R3, then I can take 2 slices of my 3 manifolds, and I can isometrically embed those 2 slices into R3. And so we have 2 parameters that we can take slices with respect to. The first one we take with respect to psi, and the second one we take with respect to phi. But as you can see, in the case of phi, we have 3 components, and we have this off-diagonal term here. And so this makes things much more difficult to embed when you have these off-diagonal terms. And so instead, I decided to set phi equal to 0, just so that we can look at what these phi embeddings would look like. And as you can see, this off-diagonal term, this g psi theta, when phi is equal to 0, then this just goes away. So then we're just left with the diagonal components, which are easy to embed. Okay, so to embed our surfaces, we assume that in R3, the embedding equations x, y, z take this form. So you just assume they take this form. Given that, we take the total derivative of these functions. And so if you take the square of those total derivatives of the functions, then that gives you the line segment in R3. And then we just take that line segment in R3, which is just the Euclidean distance, and we set that equal to the line segment that we had from our 2 slices. From there, we just set the components equal. So the isometric embedding, the equations we have to solve are just given here at the bottom. And these are pretty easy to solve. So solving these equations, we can then isometrically embed these 2 surfaces into R3. So in this instance, on this slide, you are literally looking at ignorance. This is what ignorance looks like. And so what we did is, we still have these 2 degrees of freedom, purity and lambda rho 1, so choosing a point on our curves of constant purity. And so we just decided to fix one of the lambda rho ones just so that we can, visualize these as a function of changing purity. So we have lower purity on the left, higher purity on the right. And you can see that the volumes kind of they look like they decrease, but this is just a qualitative observation just by looking at the surfaces. Some of our future analysis that we want to do would be to analyze these surfaces in more detail, but I thought it would be just fun to kind of see the geometric, what ignorance looks like geometrically. So some of the things that we want to do in our future work is we want to explain the why entropy, Rangé entropy of order 3 gives you constant volumes, meaning equivalence of ignorance. We want to explore fidelity. So, the whole point of this calculation was to explore fidelity. And so the machinery is there for it, but that's a calculation that we want to do later on, where essentially we can take these, we can take the eigenbases on the row base, the row simplex, transform them with respect to any with respect to the Euler angles in R3. Then we can compute two separate surfaces of ignorance, and we can start comparing those and kind of like seeing what it means to optimize over the set of unitaries transformations of the reservoir space. Um, Again, like I said, we want to do some more analysis where we analyze the volumes of these two manifolds and understand what their implications are. We're still not certain what we're going to do with those, but we're pretty sure we can get something out of them. We want to explore the concept of coherence in this picture. So yeah, because we're dealing with these density operators where they're defined on these simplices, which are essentially classical objects, we want to find a way of defining a clear notion of coherence in that space. And so we have some ideas on how to do that. And lastly, we think that there might be a potential for a calculation to go from a classical perspective to a quantum perspective using Bohr's notion of complementarity. So that's what we plan on doing in the future. So in conclusion, we the physical understanding of, because remember that one of the original questions was, if you take the definition of Ohmen-Joseph fidelity as being the maximum overlap between purifications, which are fiber elements essentially, what does that mean? Well, that space of where the fiber elements, where the purifications lie, I call that the space of speculation, because all you have is the constraint information in the base space. And when you go to this higher Hilbert space where the purifications lie, each purification could satisfy that constraint information. And so you're essentially left in this space where you don't know which purification is responsible. And so the more purifications there are, the more ignorant you are, the more likely you will be wrong when speculating which pure state is responsible for the information in the density operator. We use the symmetries of Euclidean 3 space to generate these fibers, because again, one of the motivations was working in R3 allows us to have a nice visual representation of what's going on. So we're able to generate these fibers and visualize them and compute their volumes in R3. We showed that volume decreased monotonically, where if you have a maximally mixed state, that's maximum uncertainty, maximum volume. And then if you have a pure state, then you have zero volume. We have this equivalence of ignorance with the Rangé entropy of order 3, which is intriguing. And I think that in the end, we were able to show a relationship between information entropy and thermal entropy, where, depending on the value of the information entropy, that then affects the number of symmetries that exist in the higher space. And so that number of symmetries captures the multiplicity associated with the macro information defined in the density operator. So this is how these two entropies are related in this context. So thank you. I really, again, appreciate you guys inviting me, and it's really an honor to come and speak back where it all began, as you will. So any questions?
Oh, that was great.
Yeah, I had more slides, but I cut them out because I thought that they might, I wanted to leave time for questions and everything. So I don't know if I sped through that too quickly.
So I have a quick question.
Go ahead.
Dr. Ferguson?
Why is ignorance orange?
Because that's the default setting of Mathematica.
Thank you.
You know, honestly, if I wanted to, I could compute the extrinsic curvature on those things and actually color them with respect to curvature. I just didn't do that.
Okay.
Yeah, the curvature of ignorance.
So other questions, discussions? I know Shannon is excited to talk about a lot of topics.
It looks like Terrence had a question.
Terrence, go ahead.
Hey, great talk. You ever thought about a geodesic through this this space that you've? Because you talk about the metric. I'm just wondering if it, just talking. What would has anybody thought about a geodesic through that space?
So actually, it's funny you asked that. In terms of geodesics on a specific manifold, I haven't really considered the geodesics in that sense, but that weird geometric mean operator that I was talking about earlier, when you're comparing two of these density operators that, because one of the images I had, you had like the fibers, the vertical lines that represented the fibers. And I think that the geometric mean operator is associated with geodesics across that larger space between these different fibers. So, and it's actually interesting you asked that too, because one of the things that we wanted to do was if we are able to have two density operators, you have a sigma simplex and a rho simplex, and we go to this higher Hilbert space, take their purification manifolds. One of the things that you can do is when computing the Ohmen-Joseph fidelity, essentially what you're doing, they're trying to line these two things up. You're trying to put them in phase. And once they're in phase with each other, when you're actually jumping from one fiber, when you're jumping from one to the other, that's actually conditioned on something called a horizontal lift condition. And that is actually the condition for geodesics, which essentially comes down to whenever you have bundle spaces, then if you're moving from one bundle to another bundle, you want to find some notion in which those bundles are considered the same. And so in this sense, the concept of kind of lining them up is associated with following the geodesic between two elements on a different fiber bundle. So, and one of the examples that I think is really good, we're just thinking about fibers in terms of tangent spaces. That is one of the things that I think is really.
So Shannon, if I may, this is Paul Olsing. Shannon and I have been working together for the last couple of years. In fact, that's a very good question, because the fidelity between two density matrices is actually defined as the shortest distance, which is a geodesic between the two density matrices in the fiber bundle itself.
Yeah.
That's what Shannon was saying.
Yep. And so, and that can also be interpreted in terms of like basically making sure that these two different fibers on the bundle are in phase with each other. So, yeah. Actually, there's an image that I have. Let me see. And maybe if I can make this clear. Yeah. Let me share the screen real quick. Yeah, this is what I mean. So if you can see here, you can look at one of these points, and the tangent space, you have curves going through this point, and each vector tangent to a curve, you have many curves that can go through that at once. And so if you have two different tangent spaces, then you want to find a way of saying that two curves are equivalent with respect to these 2 points. And so you can imagine having a curve going through this point that also goes through, that goes through this point, and then another curve that goes through this point. And in this case, the tangent vectors associated with this curve and the tangent vector associated with this curve are not in phase, but in this case, they are in phase. And this would be like a geodesic condition. And this is what you would have to do when this is essentially what Fidelity is asking you to do when you're comparing these manifolds of ignorance. Any other questions?
Other questions, topics to discuss?
or we can just chat for 15 minutes if you want. I haven't seen you guys in forever.
Well, I do have a question, but it's a little bit off subject in the sense that I know that while you were here, there was actually no one teaching or no one doing research in general relativity or anything. But I know that that topic had excited you and you found a very good university to go study it. So what was your feeling about how well you were prepared in that subject that you liked so well, given that, well, like any school, we don't have a professor in physics of every discipline or sub-discipline. So how well prepared do you think you were?
Oh, well, actually, I was actually pretty well prepared. Before I went from Wichita State to FAU, I actually took differential geometry from Dr. Jeffries. And I remember I told myself that if I can't pass her class, then I'll do something else because, I'm going to be doing differential geometry. And I actually really liked her class. And so when I actually showed up, even though I struggled through her class, when I showed up for GR at FAU, I was actually really well prepared. Luckily enough. Yeah.
Great. Glad to hear that.
Yep.
I'll ask questions, Richard.
Go for it.
Tell me about your how you were able to land your current role after you got your PhD from FAU.
Oh yeah. So when I was at FAU, I would go up over the summer at the Air Force Research Lab where Paul resides. And that's actually where Paul and I first met and started collaborating and working together. And so, because my advisor had a relationship with the Air Force. And so afterwards, I knew that there was something called the National Research Council Fellow that you could get. And so I applied for that to work at the lab with Paul, and everything worked out, and I ended up there. So that's how. I guess you can say it's through networking and yeah. I suppose that's how.
And a little bit of ability, probably.
Yeah, a little bit. Yeah, it's good to actually know math. Yeah. Yep.
Well, math is the queen of our science. So yeah, without it, you're handicapped.
Who's the king?
Hmm?
Who's the king?
Oh, that's obviously physics.
Oh, okay. I see.
I was going to say astrophysics, but I won't. Never mind.
Why? How come I can't see your lovely face?
He has a hidden. Sorry.
Yeah, there it is.
I just had it turned off,
Too scared to face me, I see.
No. Although I have to admit, you had me at slide one, like, okay, he's good, I'm done.
So if I may say something about Shannon, we're in the Air Force, but in the DoD in general, we have a very robust summer program for faculty as well as students that people can come and actually work in the lab. This year has been a little bit different. People have been working remotely due to COVID. But Shannon came in through his advisor through these summer programs, and that's how I got to know Shannon. And then there is a National Research Council Fellowship postdoc that you can apply for afterwards. And it's a national competition, but you must work in one of the labs. And there's a lot of good science going on in the research labs in both the Air Force, the Army, and the Navy. So I encouraged Shannon to do that, and he wrote a proposal, and it was accepted. And he's been 3 years doing that, and he's moved on to another postdoc position, but we're trying to do our best to make things a little more permanent. So
Hopefully.
but that's just an encouragement to other people to think about these programs when they're looking to place students. So it's not just theory, it's experimental as well as, so they're called the SFFP, Summer Faculty Fellowship Program, that you can just Google. And the one that we have locally is called the VFRP, which is the Visiting Faculty Fellowship Program. And if you want to know more, just contact Shannon. We can get you the information for that.
And actually, Paul, Howard came and gave a talk at WSU once, and he met Dr. Behrman, and he actually wanted to collaborate with her. So I don't know.
Yeah, I know. So it's a great program that we have, and that's how Shannon got involved in the whole thing, both the summer programs and then through the fellowship program. So
yeah, and it's really great. I mean, we do really, and I really enjoy working there and doing research there. So that's a nice place to work.
So if you're at an Air Force research lab, what do you do for the Air Force?
I study quantum fidelity.
Okay.
Yeah, I mean, the last paper was on quantum illumination. You know, the Air Force is interested in that, and
Well, that was my. Why is the Air Force interested in that? Interested in that? That seems highly.
Now NASA's getting involved in interest in quantum information as well.
yeah. Well, the thing is the problem is when you're setting up quantum information protocols, actually distinguishing quantum states is one of the most important aspects. And so one of the things is if you're creating a device, you know, like we create at the lab, you want to have some sort of protocol to verify it and to make sure that you understand that it's computing the correct thing. If you know, if you're writing an algorithm, you want to make sure that the fidelity of the states that are produced are what they're supposed to be. And fidelity itself is actually quite complicated. And sometimes people aren't certain which fidelity to use. Like you use different fidelities depending on the physical system you're analyzing. You change the fidelity depending on so you can use simplified fidelities, because actually computing the Omen-Jota fidelity is a bit of a pain. It's actually very computationally restrictive. And so having simplified fidelity measures and knowing when to use them is actually quite important.
Yeah, I had a question.
Yep.
I mean, it's from the little I know anyway, it seems like a big leap from general relativity to quantum information. But I know there have been these results like the entropy of a black hole, where information theory and the general relativity come together. Is there any connection that you've seen? You'd be in the place to say, I guess.
So I haven't done any direct calculations, but Paul, on the other hand, this is his bread and butter.
It's part of my fun physics, but I would say that's one of the reasons why I was interested in bringing Shannon into is to get that geometric insight. And it's a very good question that you ask. And one of the leaders in the field who literally wrote the book, Mike Nilsson, long ago showed that you could think about, even in quantum computation, the most efficient way to decompose a unitary could be thought of geometrically as a geodesic in some higher Hilbert space. And there are many ways that you could decompose this optimally, but the most optimal one is a geodesic. So one of the flavors that I've always been interested in, and why I was interested in Warner Miller, which was Shannon's advisor, and then Shannon himself, was this geometric perspective. And it's sort of a generalization of this information probability that people do classically, now taken over to quantum. And so we thought the geometric approach would give us some new insight. And that's a lot of the flavor of what you see Shannon doing in his research. You know, can we gain some other insight? Because these measures of entanglement, we only understand for what we call bipartite system, two systems that you can divide into two. And we have analytic formulas for them for bipartite systems, but not for tripartite and higher. So we always have felt instinctively that we should be able to learn something from this geometry, even by looking at small systems, like Shannon's been doing, like Qubit systems, 3-level systems, that we can get some insight and then try to generalize that.
Yeah. And actually one thing that from what Paul is saying, the von Neumann entropy of a pure, so if you take a pure state and then take a partial trace, so, you know, where the mixed states that we were treating in the talk, you can always treat them as being marginal states of some higher pure state. And if you actually compute the von Neumann entropy of that, that's actually an entanglement measure. It's called the entanglement entropy. And so there's this relationship between these volumes is actually related to entanglement. So yeah.
Do these techniques throw any light on why the entropy of a black hole should be proportional to the surface area instead of the volume, or similar techniques?
I don't know. I haven't studied that in detail, so I don't know.
It seemed a surprising thing.
We will be having coming up, Tom, a speaker, who's our welcome speaker, Professor Carlo Rivalli.
Oh,
he's going to be talking about black holes in quantum theory. Can black holes become white holes? And so there you have this talk coming up on April 27th and April 27th.
Oh, that would be nice to hear. Shannon, you get the link for that.
Okay.
It's the same link as you're using for this.
Okay. All right.
Welcome to join us.
Because that is a thing that has also been found that is a generic feature that I think appears in the case of black holes, that there are at boundaries, you do see concentration of entanglement at the boundary. So the question that you're asking, this is what someone said before, this is what quantum information is sort of bringing to those kind of questions. In some sense, it's these same questions about splitting a system in two and then asking, as Shannon has been looking about the entanglement. The difference with the black hole is the horizon and you can't see behind it. So then what can you say about that? That's the new complication. But people have studied that has influenced a lot of quantum information, and quantum information is also now going back and seeing how that might be able to illuminate those kind of questions for the black hole information problem as well. So it's all tied together of this. How do you define the missing information between two systems? And that's, I wouldn't say Shannon is doing black hole stuff, but I would say that those kind of questions help address the questions that other people are asking for those type of problems as well. So
Interesting.
Yeah, I actually have found quite a bit of overlap with my PhD work and what I'm doing now. It's all the same stuff eventually. If you tie everything to geometry, you find out the techniques. I remember one day I was reading Geometry of Quantum States by Zukowski, and there was a section where I started reading, like, wait a minute, this is exactly what I was doing for my PhD. So yeah, there's a lot of overlap. But that analysis is something that would be too far down the line, and probably something I can only do in my free time if I had the chance.
Can you say anything else about some of your other, do you wish to say anything else about some of your other free time activities?
Oh, well, I have you been listening to the podcast?
I've heard some of them.
Yeah. So I did start, oh, I'm sorry.
Not as many as I'd like, let's say that.
Oh, okay. Well, that's good, because that means that that you would like to listen to more. But yeah, so I did start a podcast. If anyone's interested, it's called the Bottom Turtle Podcast. I don't recommend starting on episode 1 because we didn't know what we were doing, as it's kind of a slog. Start from episode 2, and then and then get through the catalog. And if you feel like you have to listen to episode 1, listen to it then, because at that point you will understand pretty much everything in it. So yeah, if anyone's interested, I would be, more than happy to have you guys check it out.
Okay, great.
Hmm.
Other questions? Next week's speaker is going to be from University of Colorado School of Mines, talking about the high energetic cosmic rays and their origins and observing them. And then we have a huge, complete set of other talks coming up all the way till the end of the seminar series, ending with Carlo Rivalli as the Watkins speaker, who's had 4 books, and he's doing a lot of research on quantum gravity and quantum states information. So
I actually have several.
thank you, Ray. Thank you, Shannon, Ray, again.
Yeah.